is that nice road of stars that crosses the night sky, most prominent in the Sagittarius direction. This is a picture of our galaxy as seen edge on. You can see in the middle the center of our galaxy, and other relevant features like the Pleiades or some nebulae related to the star-forming regions. The brightest part is clearly the center of the galaxy, which we decide to set as the central longitude of our side of the sky. Herschel was the first to make a picture of our galaxy, where the sun is set more or less at the center and the rest appears as a blob of stars. In the 18th century, right before William Herschel, Thomas Wright had the good idea that the Milky Way was a flattened disk of stars, and some of the nebula visible are just separate Milky Way. That's the first time that the hypothesis of multiple uh, galaxies arise. By the end of the 18th century, Messier creates its famous list of objects, M1, M2, M3, and among them there were many, many nebulae, and some of them were galaxies. Nearly at the same time, Lord Rosse had the first sketch of a galaxy, and this is how the galaxy looks like in a picture of Hubble. Then we wait for 100 and more years until 1917, when Heber Curtis for the first time measures the distance to the nearby galaxy Andromeda. At this moment the debate was born. Were these galaxies other universes, and they were called island universes, or were they all included in our Milky Way? This was a huge discussion called the Great Debate, which involved mainly uh, Edwin Hubble and Harlow Shapley. 3 years after, Edwin Hubble could prove that all the nebula shown in some picture were actually galaxies, so the universe becomes enormous. What emerges clearly by looking at our galaxy is that the stars are blue and young inside the spiral arms, and while a lot of globular clusters, which are smaller groups of stars, surround all the galaxy. Other oval clusters, like the Pleiades, are put here and there, and they are nice and blue. Then there is dust and gas and a giant supermassive black hole in the center. Interstellar dust is made of carbon and silicates, and outside it has a nice coat. Facts of dust become clear when looking at this picture. It is red. The Bok globules are star-forming regions inside our galaxy. As you can see, the spots are the Bok globules. Then what happens to the dust? Light comes in and gets scattered. Blue light is scattered more efficiently than red light. And then some damping in the intensity acts. So there is reddening and extinction. It's more or less what happens at sunset with the sun. As a result, all the pictures taken nearby the galactic plane or the galactic center look more red than they should be, and even fainter than they should be. This is one of the reasons why we don't see clearly a bright spot in the sky, because the center of our galaxy should be brighter than our sun, or at least as bright as our sun. So it should be bright even during the day. But since there is absorption from interstellar dust, then we have no bright nights in this case. The second large component of our galaxy is the interstellar gas, which is mainly hydrogen and 90% hydrogen, and the rest, 10%, is helium. Nice colors depend on how light is made in the gas clouds. In this nice picture, the red region is related to the ionized hydrogen. The blue region is reflected light from surrounding clouds, and the dark regions in the middle are dust. Then how do we know how our galaxy is made? We know that it is a spiral galaxy, but it is very hard to tell how a galaxy is made while being inside this galaxy. To map our galaxy, we use a particular emission related to an effect which is called spin flip. Inside hydrogen atoms, the spin of protons and electrons can flip, and this flip makes a radio emission at a precise wavelength of 21 centimeters. Despite this is a very rare transition, since there are so many hydrogen atoms out there, we have a clear emission from the interstellar matter. This emission turns out to be a sort of ecography of our galaxy. In this picture you see the center of our galaxy in blue and our position in yellow. With the help of Doppler shift, one can tell what is the velocity of the cloud we are looking at. In this picture we have four different clouds of different intensity. The A cloud is much more intense than the B and C and D clouds. Here the sun's angular velocity is set to 0, so clouds moving faster than the sun are standing to the right of the central line, while clouds moving slower than the sun are standing on the left side of the line. So cloud D is moving slower than the sun. With the help of these measurements, we can tell more or less what is the structure of our galaxy and what is the sun's position in this galaxy. The whole diameter of our galaxy is almost 100,000 light years, so it is a wide object. You see the galaxy edge on, you see that there are many globular clusters distributed along a sort of sphere. And you see also that the center of our galaxy is more dense in terms of stars. It is called the bulge. And the rest is disposed as a disk. If you want to compare the size of our galaxy with the size of our solar system, think to a small penny compared to the whole size of the western US states. It's incredibly extended. Harlow Shapley used the distribution of globular clusters to obtain for the first time that the Sun was not the center of our galaxy. With the help of globular clusters, Harlow Shapley could not only tell what was the position of the Sun related to the galactic center, but also it could measure for the first time the speed of the Sun. The Sun is rotating around the center of our galaxy, and the speed is around 200 kilometers per second. It turns out that the whole galaxy is rotating. Then when you deal with rotation and gravity, you have to remember that the centrifugal force has to be balanced by the gravitational force. So you have a simple formula relating the velocity of rotation and the mass of the system. Here a first issue arises. The sun velocity is larger than it should be. It means that something strange is going on. In general, the observed velocity is larger than expected. At this stage, scientists have only two chances. One is you completely destroy Newtonian physics and gravity as we know so far. And the other possibility is that there is a fraction of matter which we don't see, but it's acting with its gravity on the galactic rotation. We call this matter, this invisible matter, dark matter. Another feature of our galaxy is about the star population. There are population 1 stars, which are young stars in ordered motion along the galactic disk. Then there are population 2 stars, which are older stars with random motion and with orbits very, very tilted with respect to the galactic plane. Then astronomers are seeking for population 3 stars that could be the very progenitors of all the stars in our galaxy. On the other hand, while looking at the center of our galaxy, we find a strong radio emission, like in this picture. Tracking the orbits of stars around this strong radio emission, it turns out that there should be a very compact, very massive object in the middle of this picture. The mass of this object has to be 1 million solar masses. To be more precise, the size of this object has to be like 4 million solar masses. And this has to be the center of our galaxy, hosting a huge object, a dark object, that is probably a large black hole.